Hello, everyone. Welcome back to SAT Math Question of the Day. Here's our question, and if you hold on later, we do Throwback Thursday, which we'll explain later. Here's our question of the day. Please try it yourself, pause, come back, and we will hopefully give you different approaches on how to do it. Okay, point O is the center of a circle. What is the value of x? Okay, what is the value of x? Obviously, this is a geometry problem, and it's related to a circle. That's value x.
So my very first approach is to draw these lines.
No, my first approach is to understand this is an angle puzzle. And in an angle puzzle, write down everything you know as fast as you can.
Yeah.
Okay, just start throwing stuff in and then hope for the best. That's how I approach angle puzzles. Circle, it's a circle angle puzzle.
Yeah.
Wow. Look at that. 20 degrees. Yeah. So you're saying this is 40 degrees here, because the angle is 1/2 of its intercepted arc.
What angle? Okay. Right? Let me draw in what angle we're talking about.
This is, okay, if you have a theta and you have an 80.
No, let me draw. I'm going to draw it right on the diagram. Okay. Here we go. I'm going to use. Draw write in your angle in blue, and I will.
Blue. Okay, blue.
Put in blue. I'm going to use blue or purple. And okay.
Blue. Yeah, blue.
What is 40 degrees? What is 40 degrees?
40 degrees is the angular measure
the angle
of the arc, the intercepted arc.
Okay, how much is
it's
the angle of the intercepted arc?
Yeah.
Is the angle that is between the radii, in other words, lines from the center to the ends of the arc. So the angle in that diagram that is 40 degrees is this little angle.
Yeah, but we don't need that right now.
But we have to know. But the thing is, the insight of drawing the red line, the two red lines, is that what's helpful is the angle going around here.
Yeah.
Which is 40 plus 80.
Right. So that's 120.
Is 120.
That's right. That's 120. Right. Yeah.
And so this angle here is 120. Right.
This angle here. Yeah.
This angle.
Yeah, this angle.
And therefore, because it's these are the what's called transverse angles of intersecting lines. Transverse angles are equal.
Right.
So the angle that the question is asking for.
Right.
In other words, x is also 120 degrees.
Right. Now it's a little.
That's the answer.
Yeah. It's a little bit hard to see that that's a vertical angle. So let's just show that, and then we'll come back to this undo. So let's show that more clearly, because that's hard to see, isn't it? Again, really, right? Because here, let's make it. We'll do it, and then we'll come back. We'll undo it. This is a black line.
We're gonna put back my. Oh, come on.
There you go. See that? So if this is 120, then this is 120. See, they really are vertical angles, but it's hard to
vertical angles?
Transverse angles, opposite angles, whatever you want to call them. Two angles cross, two lines cross, AB. A equals B. Angle A equals angle B. Yeah. But you had to use 3 geometry theorems here, 3 geometric relations. One, the in a circle, the intercepted arc, let's call it 100. If it's 100 degrees, it is double the inscribed angle. This is called the inscribed angle, the angle on an edge of the circle, the outside of the circle. This is one theorem. The second theorem that Seth used was the angle, the measure of an intercepted arc, if this is 100 degrees, then it's called the central angle. The angle that the radii make from the center to the intercepted arc is equal to the the angular measure of the intercepted arc. So that's another one.
Yeah.
And then then that's how you got this was 120. And then we used the fact that they're vertical angles. So it's a 3-step problem. And I think a good approach, which we Seth both and I both did, was just calculate stuff you know. You never really had to know that this was 40, did you? You never really needed to know that was 40.
Well, I wanted to know that because I wanted to be aware that when you drew this angle measure, this angle measure around an arc, how the hell is an arc, a curve, have a measure that's an angle? It has a length.
Well, there are two ways.
A length.
Yes,
But what we consider the angle measure of an arc of a circle, that means the measure of the angle between the radii of this. In other words, this 100 is the measure of what Joel called the central angle subtending the arc.
But those are all words, but what's really going on is it's really a ratio of how much it is compared to an entire circle. Because someone said years ago, Seth, you may know history more than I do, that someone said a circle has 360 degrees. Maybe it's from Egypt because they were into sixes back then. So it really is, it's really a ratio. It's 100 degrees out of 360 degrees. That's the real essence of what we're
But it's important conceptually to distinguish between measures of length and measures of angle.
Absolutely right. Oh my God, such important.
And what bothered me is confusing them.
No, yeah. You've got arc,
and that is why that in order to relate, what the insight that I had is we are going to combine. We're going to combine arcs of the circumference, and we are going to relate them to angles. And the way an arc of a circumference is related to an angle is via the central angle. Yes. And therefore, I drew the relevant radii in red.
Yes.
And that is why I'm interested in saying that the central angle for let's call it B prime. The central angle for B prime C is 40 degrees.
Right. Yeah. That's fine. But in the end, what you really wanted,
the central angle subtending arc B prime C has measure 40 degrees.
Yeah. Okay. Fine. You can do that the way you want. But
and then the theorem about central angles versus inscribed angles. That for the same arc, the central angle is twice the measure of the inscribed angle.
Right. Yeah, we said that already.
Yeah.
Now,
but I'm saying it again because that is one of the several facts.
Yes.
That's relevant in this problem.
Yeah. Now, Seth beat me to it when he drew those red auxiliary lines. I'll put them in green. Auxiliary lines. See, Seth drew those in there. Seth beat
Yeah.
me to it. I would have had to think a little bit about what to do. So that comes from experience. We know that there's an inscribed angle. Once you see an inscribed angle type thing here, it's important to remember that there's that theorem having to do with the subtended arcs. The only way you can subtend the arc is by doing what Seth did, which was make what's called an auxiliary line. Now we're talking, right? Now there's something we can calculate, which is this angular measure, which is 40, which is helpful. Seth beat me to the auxiliary lines. I can't say how long it would have taken me to realize to do that. Probably not that long.
Well, what bugged me about the question when I first saw it, is that the figure that they presented had this sort of bald, as in my head, no hair on it, figure, quadrilateral, non-convex quadrilateral.
Right. Yeah.
And where they told us two angles, and there's no information.
That's right. Yeah. Now Seth, I think, got a jump start.
Except this is the center. Right. So there are other approaches.
Yeah.
But since we're dealing with these angles, see this angle are in the problem, and then the third angle is this one. In order to relate the angle involving line 1 and 2 to the angle involving line 1 and 3, I needed to have some common line between 1, 3, and 2.
Yeah.
Right.
So
again, seeing these angles, like seeing these, I figured that it's I can't get too far by analyzing simply the quadrilateral. It's critical to make use of the fact that it's inscribed in the circle.
Right. That's right. That's a good thinking process. Now, however, I'm going to accuse
it's most critical. That it's inscribed in a circle, and this vertex is the center.
Right. Yeah.
Of the circle. Yeah.
Now I'm going to accuse Seth of cheating a little bit, because we have a pact, but sometimes we break the pact where we don't look at the question ahead of time. But as I was bringing it up on the screen, Seth's brain was already thinking about it. So Seth got it.
Well, once you see the picture, it's hard not to think about it.
No, it's not. It's not hard. Have a little self-discipline. Just don't think about it.
I don't have self-discipline. When I see a picture, I automatically think about it.
Okay. Well, then what's funny is that when we do Throwback Thursday question, I looked at we're going to get you back, because I looked at the questions when I shouldn't have either. This is just an ideal goal, but Seth and I always break it. But in this case, that's why Seth jumped ahead of me, and Seth knew how to do it faster than I did. Okay, anyway, but Seth's right. As soon as you see a question, you start thinking, and Seth's logic was very right. It doesn't really help. You don't have enough information just given a four-sided figure. That, by the way, all the angles add up to 360 in a four-sided figure. This doesn't really help you because you only have two angles, so you have to bring in something else. Auxiliary lines, be ready for those. Okay, so what do we say, 120? So let's see how they do it. Again, this is a geometry puzzle. There are multiple ways to do a geometry puzzle. Let's see how they do it. They probably do it the same way. We'll see. We'll find out. 120 degrees, right? Ooh, I see X has a unit of degrees. Okay, we always look for units. We always make sure. Okay, hint for the problem. So that's 5 hints. So let's put them all down. Don't cheat looking at them, Seth. It's enough you cheated enough once.
2 steps.
My God, 5 steps.
5 steps. Come on.
Okay, well, we had to use, 3 theorem? No, we had to use a 4th theorem, which everyone forgets. It's the angle addition postulate. Or the segment addition postulate, didn't we? Remember we had to add the 40 and the 1 and the 80 to get 120? That's actually a postulate in geometry they also use, but it's so incredibly obvious that we won't even talk about it.
Nothing's incredibly obvious.
What? The angle addition postulate and segment addition postulate? You have two things?
Nothing is incredibly obvious.
Yeah, but we had to use that also in this theorem. So we actually had to use 4 things to do this problem. At least 4 things. Okay, we can use our knowledge of angle relationships to find the value of x. The SAT gives us the following relevant information. Oh, yeah, I'm sorry, yes. That is your reference sheet from the SAT, okay? So they reference that. The number of degrees in an arc is 360. Okay, so remember, this is given to you on your reference sheet. Okay, the sum of the measures, degrees in a triangle is 180. Really? They give that to you? Oh, yeah, look at that. They give it to you. Triangle. How are they? Oh, I don't like the way this is going. Because we never use that. But I like the way this is going because they're using a different approach. Isosceles triangles. Oh, they're using the all radii are equal thing. The sum of the measures of an angle. Oh my goodness.
Oh, that's a different approach.
Yeah, this is a whole different approach.
Oh yeah.
So what they did is they drew an auxiliary line. They created a second radii. A third. They created a third radii, and then they used the fact that all radii are equal, and that tells us that those two triangles are isosceles, which then gives you the 2 leg angles are the same. And then you can get the other angles by figuring out that they this angle here is 180 minus 80, and this angle here, use different colors. Angle red is 180 minus 40. It's nice to use different colors. And green is 180 minus 80. Right? Oh, the measure of ACB. How do they do it then? ACB is 60. Oh, I see. So they got ACB was 60. And then what did they do? Oh, so they got the third angle in a quadrilateral.
Yeah.
So they did it differently from even how I mentioned.
Yeah.
Wow, so there's a third way to do it. They got this angle, and then they used that this is a 60, 20, 40, messy Joel, and then you get this one, and then, my God, so that's another way of doing it.
Yeah.
Wow.
Well, here's, I see, please keep the figure on status, scribble on it.
Right there?
Okay.
Right there?
Here is, yeah. Go back to the previous figure.
Sure.
Under 2.5.
Yeah, sure.
Good.
Right there.
Now I see yet another approach from this idea. You see, again, following that idea of drawing the radii. Come on, I don't want to use black there. Yeah. I'm going to draw a radii. This radius.
Right, yeah.
And yeah. So what happens is, what I see this approach is that we have, isosceles triangle. Therefore, the central angle of this is 40 degrees because it's twice 20 degrees.
Yeah. No.
Similarly, the central angle of this arc, right,
is 80.
Is also
80.
Twice 40 degrees,
which is 80. Yeah.
Right.
Right.
So we have twice 20.
Right.
Plus twice 40.
Yeah.
Is equal to 40 plus 80, 120.
Yep. I always sort of joke, but it's not really a joke. In geometry, when in doubt, drop perpendiculars, okay, and all radii are equal. Now, this little cute little thing, you wouldn't believe how this little quip helps you in a lot of geometry problems. When in doubt, which, by the way, you're highly in doubt because you look at this question, you have no idea how to do it. When in doubt, drop perpendiculars. Well, that doesn't really apply. And all radii are equal. All radii are equal may remind you that you can draw an auxiliary line, which is a radii, and all of a sudden, all radii are equal, which means that these are equal. Oh, yeah, they're all equal, right? Yeah. Which means that all these are equal, which means all the triangles are isosceles. So, this little quip, when in doubt, drop perpendiculars and all radii are equal. And then I also say, we won't do it, when you're really in trouble, really in trouble with geometry problem, look for similar triangles. Because very often the similar triangle problems are the hardest to spot. So, when in doubt, drop perpendiculars, all radii are equal, and when really in trouble, look for similar triangles. But the bottom line is there are at least three, maybe. Wow, there are a lot of ways to do these angle puzzles. It's good that they did it a way that we didn't do. So it's
yes, indeed. Way. That's cool. That's cool. All right, good.
Yeah, that's a good way of doing it. That's a good way of doing it. Okay, great, and everything else goes there. Time saver. Ooh, time saver. They used the approach we did. We can use the inscribed angle theorem to save us some time, since this. Since ACB is an inscribed angle.
Okay. So they didn't use their approach did not use the inscribed angle theorem.
Oh wait, since ACB is an inscribed angle,
we could save time by using it. Well, the relationship.
Oh yeah. Right. Once they realize that's right. Once you realize that this is 60, then immediately know that that's 120.
Now, you know how to prove the inscribed angle theorem.
No, but that probably
it is very important to know how to prove the inscribed angle theorem, Joel, and I'm going to do it.
Okay,
whether you like it or not.
I think I can figure out.
I will show you how to prove the inscribed angle theorem.
That's a nice circle.
Here it is. You have here's your setup. You have a central angle.
Yep.
Right?
Yep.
And then you form an inscribed angle like this by one of the inscribed angles for the same arc is the one in blue.
Right. Okay.
Right?
Yeah.
Now, what we have seen, what we just saw, is that all of these three lines marked in blue are three different radii.
Right.
And in a circle, every radius is equal to every other radius.
All radii are equal, right. Yeah.
And therefore, this angle, the inscribed angle, the inscribed angle here
right,
is equal to the angle here because they're isosceles triangles.
Absolutely.
And therefore, the central angle supplementary to the red inscribed angle is 180 minus 2i.
Right. Okay.
Right?
Right.
And then what is the inscribed angle? The inscribed angle between the reds is 180 minus 180 minus 2i. And the 180s cancel and the minuses cancel and you get 2i.
Okay, I didn't follow you. When you said the inscribed angle, didn't you mean the central angle? You said
there are two equal angles I, which are
right,
which are inscribed.
That's right.
The question mark angle is a central angle.
That's right, the central angle.
And the supplement of the question mark angle is another inscribed angle.
The supplement to
So
the
what I
question
did
mark.
was,
Wait. As a supplement to the question mark angle
yeah,
is another inscribed.
yeah, that's because the center of these angles is the center of the circle,
Right.
right? And what I did was give this blue line is a diameter,
Right.
right?
Right. Yeah, but
Right?
it doesn't have to be a diameter.
No, it is a
Doesn't
diameter
doesn't have
because
to be.
we're talking about the relationship between a central angle and another angle. So for
Seth, but it doesn't
us
have
to
to
talk
be.
about a
Seth,
central angle, we
Seth,
need
Seth,
to
Seth,
draw it from
Seth,
the
Seth, Seth,
center.
Seth. It doesn't have to be a
Yes,
diameter.
indeed. Yeah.
You
Now,
can
another
draw it.
problem.
You could draw it this way. You could draw it this way. There's no diameter.
Yeah.
Okay.
Now,
So this is two. This is
here
right.
is the case where the inscribed angle shares an edge with the central angle, but there's a generalization of this theorem is that you'll use a different color. Is that we took another inscribed angle, subtending the same arc.
Right.
This other inscribed angle, well, how do you know that it has the same question mark measure? Right?
Right.
No, the same measure I.
Right.
How do you know that this angle here is equal to this angle
you probably
there?
use some sort of congruent triangle thing.
Nope.
No.
They're not congruent triangles.
No, they're not congruent triangles.
Yeah.
They're similar triangles.
No, they're not. They're not similar either.
Oh, they're not similar?
Nope. Can't be similar.
Wait. These two triangles are similar, though. This triangle here and this triangle here, they really are similar because they have the vertical angles and they have two equal angles. I mean, in the end, they are. Maybe we haven't proven it yet, but they are similar.
No.
Aren't they?
No way. Well,
Anyway.
I'll draw an extreme example.
If you also want to look on how to do this, look in your geometry textbook.
Yeah.
Because your geometry textbook also shows you how to prove that an inscribed angle is half of its intercepted arc.
Okay, let's say we have two points on the circle, and let's draw two inscribed angles. Is this one? And I'll draw a red one.
Yeah.
Okay.
Right. Okay.
Now,
how do you know they're the same?
In this example, the two inscribed angles, they are equal.
Okay. How do you know that?
Because they subtend the same arc.
That's circular reasoning.
No, I'm not. I'm saying what I'm demonstrating is an example that obviously shows that the two triangles are not similar. The purple triangle and the red triangle are in this example shows that they are obviously not similar.
No. We're looking at different triangles, Seth. These are similar. They are similar. This triangle here, the orange triangle there, and the black triangle here, they are similar, aren't they? Because these two angles are the same, and then these are vertical angles.
Oh yeah. That's true. That happens. Yeah. Oh yeah. That works. Yes, indeed. That's called the butterfly.
Yeah.
Oh yeah, sure.
Anyway, so maybe we should move on.
Oh, indeed. Yeah. So your argument that the butterfly wings are similar triangles demonstrates that any two inscribed angles subtending the same arc are equal.
Okay, I think we should move on. And frankly, Seth,
Okay.
you haven't proven it in an organized way. But so why don't we just say, look, if you care, go to your textbook. Go to your textbook. I don't like the way we do it.
All right, so move on to throwback.
I don't think it was tight enough, okay, and organized enough. When you do geometry proofs, you really want to be organized. Go to your textbook if you want to see how it's done. Okay, so that's it for now. Let's introduce ourselves. This is Seth Chaiken, Brothers Joel. Seth is a PhD in math from MIT. He's a professor emeritus at State University of New York at Albany. Joel, I have a PhD in mechanical engineering. We have different approaches to problems. We're here to offer different approaches on how to do math SAT questions and also how to approach studying for the math SAT. A good way to study for the math SAT is to take a Khan Academy course. Just go to Khan Academy, look for their courses. There's the digital, non-digital side. Take the course that is that your guidance counselor says. Talk to your guidance counselor as to which test you're going to take because the SAT is changing in the next few years. And on Thursday, we go back to tests that predate the 2016 SAT when the SAT moved to more a test, at least on the math side, of what you learned in school as opposed to reasoning and IQ type stuff. So we are going to go back to a pre-2016 test. They look different. There are some math questions that look different. They have this crazy type of question which was a comparison question where you have to look at column A, look at column B, and if column A is greater, you answer column A. If column B is greater, you say column B. If the two quantities equal C, and if you can't tell the relationship between the two, you answer D. So we have at least one of these today. Maybe we could do both, but let's at least start with this one. Now, this is the one I cheated on because I looked at it when I shouldn't have. Okay, so here it is. P, Q, and R are consecutive integers, and P times Q times R is equal to 0. Which is greater, the greatest of P, Q, and R, or 0? So this is like an analysis number theory question. It seemed to me that one of those numbers, P, Q, and R, one of those numbers has got to be 0. Otherwise, when you multiply them, you get 0. At least one of those numbers has to be 0. So if one of those numbers is greater than 0,
okay, here we go.
P, Q, and R can be negative or positive. So maybe the answer is
anything
D.
Anything goes.
Yeah, anything goes.
So one of these numbers is 0. Here's the number line.
Right.
Here's 0. One of these numbers is 0. And they're consecutive. So one possibility is ... Another is ... And the other possibility is ... Right?
Right. Yeah.
And here, the greatest. Here, the greatest is 0. Here, the greatest is 1. And here, the greatest is 2.
Oh, yeah. So you can't tell, but
so
that's
we
interesting.
Cannot.
So in other words.
So all of them, in all cases, the greatest is greater than 0 or equal to 0.
Wow. Oh, so D is right, but for the wrong reason.
The greatest of these things is always greater than or equal to 0. Right? And so, what? They don't give the option.
No, it has to be strictly
so
greater.
A is greater than or equal.
Right. Oh, wow. I thought P, Q, and R, one of them can be negative, but I was
They're
wrong. They're consecutive
Wait.
integers, yeah.
No, they integers. They could be negative.
They could be negative.
Yeah. So again, what do these dots mean? Case 1 is PQR.
Yep.
PQR equals -2, -1, 0. The other case is -1, 0, +1. And the other case is 0, 1, 2. Here, the greatest is 0. Greatest is 0, greatest is 1, greatest is 2. And so, only 3 cases. This quantity depends on P, Q, and R.
Yeah.
It's not a single number, not well determined. And whatever number it is greater than 0 or equal to 0.
Right. Yeah. I thought it was.
And it is column A.
Right.
And the best we have is not the best. If they gave us a choice, column A is greater, which isn't always true.
Right. Yeah. I looked at
and certainly the number in column B, 0 is greater than any of these. And that's false.
Yeah.
The two quantities are equal. It doesn't have to be.
Right.
Because we can have 1 and 2 compared with 0. This is a faulty question.
No, it's not a faulty question.
There's no the relationship can be determined.
Oh, I see.
But they don't give you a choice of the correct relationship.
Ooh, you're right. Maybe that's why in 2016 they dropped the stupid question type. Yeah. The answer, I'm looking at I actually have the answers here. The answer is D. Wow, so I would have gotten it right, but for the wrong reason, because I said P, Q, and R could be anything they want to be. That's completely untrue. They have to, the greatest of P, Q, and R has to be, in other words, the greatest of P, Q, and R can't be less than 0, right? Cannot be negative.
Yeah, so that's because one of them must be 0.
Right.
And they are consecutive.
Right.
Yeah.
So, should we try?
And there are 3 of them.
Let's try one more since we're here.
Yeah.
Let's try to do it quickly. So the greatest power. Notice these questions have a whole different feel to them from the modern SAT. Okay, here we go. So the greatest.
Let's figure it out.
No, don't forget, no calculator. I don't believe there was no calculator on the previous test. Yeah, of course there was no calculators. Nobody had access to calculators back then because they weren't that cheap.
Well, the way I handle this is I immediately see that 3 plus 7 is 10. 3 plus 7 equals 10. And 10 equals 2 times 5. And therefore, the greatest power of 2 that divides n is 2 squared times 2, which is 2 cubed.
Okay.
Now, what about this? 3 plus 5 equals 8. 8 equals 2 cubed. There's a 2 multiplying it. So the greatest power of 2 that divides this thing is 2 to the 4th. B is greater.
B is greater. So wait, this is 2.
It's twice as big.
This is 2 times 8, which is 16. 16 is 2 to the 4th. So this is 2 squared times 10. Oh, which is 2 squared times 2 times 5, which is 2 cubed times 5.
Yeah.
The greatest power of 2, that is a factor, right? Yeah, it's 2 cubed versus 2 to the 4th. Yeah, Seth did it faster than I did. That's why he has the PhD in math. Notice you can factor out stuff, right? You got the common 2, so you go 2 plus 5. If you do it the slow way like I would do, and this is 2 squared, 3 plus 7. Seth did it a lot faster than I did.
Well, it's
so
basic number theory. The basic number theory that enables you to do this fast is called prime factorization.
Right. Yeah.
The prime factorization properties.
Right. Yeah.
And together, they gave you the numbers in which common factors. They gave you a sum of numbers in which the common factors of the terms in the sum were explicitly given.
Yeah.
Right?
Yeah.
And they're common.
Right.
So you have f times a plus f times b is equal to f times a plus b.
Right.
Which is a factorization of the quantity.
Yeah.
So obviously, the quick way to approach it is to simply seeing a and b, little a and little b, and the other problem, little a prime and b prime. You just add them, yeah.
Right. Yeah. Notice that back then, but even now, look for patterns. Patterns are very important because patterns save you time, and time is of the essence in these tests. So look for patterns.
Well, I say even more. Appreciate patterns. The pattern is given to you.
Yeah, but you have to be on the lookout for it.
So here's an alternative question. Here's an alternative. Here's an alternative form. You calculated this out. It's 8 times 5 is 40. Suppose they told you n is 40, and this is how much? 8 times 16.
Yeah.
16 is smaller than 40, right?
Right.
But the greatest power of 2 that divides it, the greatest power of 2 that divides 16 is greater than the greatest power of 2 that divides 40.
I think I lost you.
16, the B number. The B number is 16.
Yeah, the B number.
The A number is 40.
16.
The A number is bigger than the B number.
That's right. Yeah, that's deceptive.
But the power of the greatest power of 2 that divides the A number is only 8. The greatest power of 2 that divides the B number is the whole B number, which is 16.
Right, exactly. That's right.
So the number they're asking for, of the numbers they're asking for, the bigger one is from B.
That's right. 40 is 8 times 5. 16 is 16 times 1. Yeah, 16 is a greater power of 2 than 8. Yeah. And probably, when I was in high school, I probably would have done it this way. Yeah. Okay. So I guess we're done, right? We really are done with Throwback Thursday. So have a great day, everyone. And we hope to see you next time we meet. And of course, like us, dislike us, please give us comments on our YouTube videos. And if you have any SAT math questions, please email them to us at satmathquestionoftheday@gmail.com. Everyone, have a great day.
Okay. Bye, everybody.
Bye.